the beginning part of this, I guess, is a little bit about differentiability, but it's more of a lead-in to what we're going to be doing soon. So we're going to differentiate. We're going to find the derivative of each function with respect to x. If you're not sure what that with respect to x means, I suppose that means you're paying attention. Like, that's okay. Right now, just think with respect to x, that means x is the input. And so I guess that's the normal course of affairs. So f of x is 1/3 x plus 1. Now I know derivative is going to give me the instantaneous rate of change, the slope at a point. So I already know the slope of this line is going to be 1/3. I've known that for a long time, you know. Maybe I should be writing f of x plus h. In fact, let's do that. Let's do f of x plus h minus f of x over x plus h minus x. Probably don't need that in this case, but whatever. So let's replace f of x plus h with 1/3 of x plus h. Replace f of x with 1/3 x, and obviously x divided, or x minus x is 0. So limit as h goes to 0, 1/3 x plus 1/3 h minus 1/3 x. Well, 1/3 x minus 1/3 x is 0. 1/3 h divided by h. We end up with the limit as h goes to 0 of 1/3, which is, of course, 1/3. So in this case, I get exactly what I expected. The derivative of the line 1/3 x plus 1, the thing that would give me instantaneous rate of change at any point, is 1/3. So what I wanted you to sketch, let's put some, I just know I'm going to need some numbers on here. So we'll do 1 there, 1, 2, 3. And normally I don't care about numbers, but in this case maybe I do. So I know f of x, 1/3 x, or 1/3 x plus 0, is going to look like this, f of x. And maybe I'll write 1/3 x, even though I don't need to. And then I need to sketch f prime of x on the same set of axes. Oh, I like that teal. So that's always 1/3. So that's f prime of x is 1/3. And all that's saying is, at any x value, the slope is 1/3. So how does that work? Well, where x equals 2, what's the slope of that red line? 1/3, which means f prime of 2 is 1/3, which gives the slope of that red line. At x equals -1/2, what's the slope of that red line? Oh, that's 1/3 as well. So we'll put, right, that means this is f of -1/2. That's also 1/3. So it's weird. I'm trying to establish ahead of time this relationship that the slope of the original f graph, in this case 1/3, is the output of the f prime graph. And if that doesn't make sense, like many things, I'm preloading, so we'll see that soon. I'm going to skip over that next one because it's a line. It's not terribly different. Maybe that's just slightly more practice. I don't know. These are basically the same. Let's jump down to j of x. Okay. So if I'm going to find j prime of x, that's going to be my formal derivative stuff. Limit as h goes to 0 of j of x plus h minus j of x over x plus h minus x. Ooh, did I throw an h in there? Ooh, I did. Make sure on this one, you do the limit. You can't do h goes to 0 of h of x plus h. That's crazy talk. Okay? You're using h for two things. H is actually a change in x. So if you look in many calculus textbooks, what you'll see is there's also a delta x approaches 0, which means the same thing. So we can say h of x plus delta x. And you treat that delta x as one variable. Talking's hard. Minus h of x over x plus delta x minus x. And if you don't catch that, no worries. Sorry. Back to j of x. Okay. So this is supposed to be j prime of x. And that's going to be equal to the limit as h approaches 0 of negative 3 times x plus h squared plus 2 minus negative 3x squared plus 2 all over h. And let's expand a little bit more. So that's going to be negative 3x squared. Normally I'd get 2xh, so that's going to be minus 6xh. H squared times negative 3 is negative 3h squared. We still have plus 2. Subtract a negative 3x squared, and that's good. That adds up with my previous negative 3x squared to 0. And then that's a minus 2, and that's good because that adds up with this 2 to get 0. Okay. I do need some parentheses. No, I don't. I could have just left that. Okay. So we're going to have limit as h goes to 0 of, what's that going to be? Well, the negative 3x squared plus 3x squared is 0. And we'll get negative 6x h divided by h is negative 6x. Minus 3h, because the h squared divided by h is going to give us 1 for numbers near 0, and then everything else goes away. And so limit as h goes to 0 of negative 6x is negative 6x. Limit as h goes to 0 of negative 3h, oh, that's just 0. Okay, so that's j prime of x. Okay, so maybe I would draw j prime of x first. So if that's 1, negative 1, we'll call this 3, negative 3. J prime of x is going to contain the point, 1/2, 3. Okay, so this right here is j prime of x, which is negative 6x. Gosh darn it. I drew positive 6x. Okay. So I'm drawing something with a slope of negative 6, not positive 6. Get it together. There we go. J prime of x is negative 6x. So now we need to go back and draw j of x. What was j of x? Negative 3x squared plus 2. Okay. So negative 3x squared plus 2 is going to have a y-intercept of 2. So maybe we'll put that on here, 0, 2. Is going to open downwards. Let's see. Where is that going to cross the x-axis? 0. The y value is 0 when the x value is something like that. Okay, that works for me. You know what? I'm just going to do this so I can be lazy. And I suppose what we're going to talk about later, what you might notice, is that j of x changes from increasing to decreasing, where j prime changes from positive to negative, because this blue graph has outputs that represent the slope of the red graph at any x value. If you don't get that, don't worry, eventually you will. Okay, so hopefully that's enough on this first set where we're doing derivative and sketching. Okay, that's kind of a lot. If you're watching this, maybe do like 3 or 4 of them. Don't worry about all 6. That's way too much work. But I suppose don't tell people. Okay. So on the latter part, kind of proving if a function is differentiable at a point or not, determine if each of the following functions has a derivative at the given value x equals c. Ooh, time for me to pick up the kids. Make sure to use the formal definition of differentiability with 2 one-sided limits. But notice we could use continuity only if, like, hey, this graph is discontinuous at a point, so I don't need to check for differentiability. Okay. Okay, so x equals 2/3 at negative 8. Now, it might help to have a sketch. You don't need a sketch, but if you did have the graph of x to the 2/3 power, and I suppose it'd be great if you knew these, but if not, you know, whatever. X to the 2/3 power has a cusp at x equals 0. Which means I'm thinking over here at negative 8, our work should indicate that f is differentiable at -8. Okay, so what is that work going to look like? Well, if f is differentiable at x equals -8, then on the left-hand side, the limit as x approaches -8 from the left of f of x minus f of -8 over x minus -8 should be equal to the limit as x approaches -8 from the right of f of x minus f of -8 over x minus -8. And remember what that means. We have an anchor point here at -8, and we're successively imagining finding slopes of secant lines with that other endpoint closer and closer to that point at -8. Anyway, so how the heck could we do that? Well, the answer is, we can kind of cheat. Okay? So our work won't look like we cheated. It'll look like we're smart, and maybe I am, but survey says probably not. Okay? Okay? Let's see. I'm realizing this is... I didn't give you the right information to make this easy enough, because in my head I'm going to do this with a fake derivative. Okay. All right. Well, we're actually going to have to come back to that when we know a little bit more, because this is going to be way too much work for the weekend. So I'll upload this. I will change the instructions, and then, we'll worry about the rest later.